Thanks for the introduction. So the topic today is on a microfluidic-based real-time detector for fine particulate matter. So the focus of my research is on fine particulate matter. So these are particulate matter smaller than 2.5 microns in diameter, otherwise known as PM2.5. So these are the most dangerous particles because they're so small they can penetrate deep into the lungs and causes a wide range of respiratory and cardiovascular problems. So normally you would see an air quality index reported in the news, and it actually corresponds to a mass concentration of PM2.5. So the US Environmental Protection Agency recommends an annual exposure limit of 12 micrograms per cubic meter. Where I'm from, in Vancouver, we don't have this problem. We're usually well below this limit. But in a busy city like Beijing, it's very common for the mass concentration to exceed the limit by 10 to 20 times. And it was estimated that simply by reducing the standard by 3 micrograms per meter cube, you can potentially save $4 to $9 billion per year in medical costs. So if it's so important, how is it measured? Well, the most standard way is to use a gravimetric analysis. So this involves drawing air through a filter to capture the particles, and then you bring the filter back into the lab to weight the filter. So while this is very accurate, it's also a very time-consuming process, and you don't get any real-time measurement. Alternatively, there are commercial optical particle counters, which can give you a real-time particle count. However, they're usually very bulky and expensive. So what we want is to develop a technology that is low cost and can sense in real time, so we can have a network of these sensors distributed over a wide area to get a local mass concentration reading. And if it's portable, we can use it as a wearable device. So you can put it on yourself to give the user a real-time feedback of their exposure level. And this is particularly important for people working in hazardous environments. So there have been some research work in this area to miniaturize these detectors. Our approach really focuses on this particular application for PM2.5 environmental sensing in real time with reasonable accuracy. So what we have is a two-part system. First, there is a microchannel which inertially sizes the particles, and the channel will output PM2.5, and this is connected to a low-cost optical particle counter. And because we're sensing individual particles, we can get a very high-resolution real-time measurement. So now let's look at how the separator works. So when this particle makes a 90 degrees turn, it will experience a inertial force, the centrifugal force, and causing it to move outwards in the radial direction to cross the streamline. And this is balanced by opposed by a viscous drag force in the opposite direction, described by Stokes' law. And by equating the two forces, you can solve for the radial terminal velocity of the particles, so this u here. And you can see from the expression that this velocity is proportional to the square of the particle diameter. So this means that as the particle size increases, it will be more and more percentage of the particles will be driven into this particle trapping region shown at the bottom, and it gets captured there. So these devices, typically the performance is described by the penetration efficiency curve shown on the right. And what this tells us is that for a particular particle size, what percentage makes it through the device. And to size PM2.5, we want to set the 50% cutoff at 2.5 microns. And the slope of this tells us how good this device is. So ideally, you want this to be a vertical straight line. So everything less than 2.5 passes through, and greater than 2.5 gets captured. So to design this device, we looked at the impactor design literature and looked at dimensions numbers, Reynolds number, Stokes number. But because this is somewhat different, the geometry is somewhat different from previous work, we had to use COMSOL simulation to simulate the flow and particle behavior. And let's take a look at that. So for particles smaller than 2.5, you can see that most of the particles has no problem passing through the channel. And now slightly greater than 2.5, initially the fast particles will be impacted. There's still some slow-moving ones making it through. So through an iterative process, we were able to optimize the geometry of the device, and based on these penetration efficiency curves. Shown here are 3 of the many curves from our simulations. So again, what we want is to set the 50% cutoff at 2.5 microns, and also we want to minimize the particle loss for smaller particles. And for larger particles, as I pointed out in the simulation, there is a percentage that gets still makes it through, and this is because these particles are traveling on the slower streamlines near the top and the bottom wall. So without 3D focusing, flow focusing, there's always going to be this problem for this device. And so we settled with design. We chose design A based on this curve here, so the purple curve. So now let's move along to the optical detector. We first looked at the light scattering theory from the particles. Because PM 2.5 is much greater than the wavelength of light, it's in the Mie scattering regime. So this means that classical optics can be applied. So the particles will diffract light, reflect light, and refract light. And this means that the scattering is also very angular dependent, with the strongest in the forward direction. So the intensity of the scattered light is given by the expression on the right. And the angular dependent term is this S theta term. To find this, you have to solve the Maxwell equation of light traveling through a spherical particle. And luckily, there are plenty of softwares out there available to do this calculation. And so the result is plotted on the right. And so this is for PM 2.5 with red laser light. And you can see most of the scattering occurs in the first 20 degrees. So based on that, we designed a low-cost forward scattering system. What we have here is light from laser diode focused by a lens onto the stream of particles coming in. And there's a light trap here that captures the laser diode, the light from the laser diode, preventing the light from directly shining into the photodiode. So the light scattered off the particle is in the forward direction in the first 20 degrees is captured by a second lens, and this gets redirected into the photodiode. And then this will register a pulse whenever there's a particle. We also try to optimize this device. We want to minimize this sensing region, the W here, and this is to maximize the optical power density from the focused light, as well as minimize the chance of having multiple particles in the sensing region at the same time. We also want to minimize this distance at between the sensing region and the photodiode, and this is from the D squared term here in the scattering light intensity. So all these parts are commercially available. We use ray tracing software to work out the alignment, and then finally everything is mounted on a 3D printed enclosure. So it was very simple to assemble. So both the separator and the detector was tested with a reference instrument, the aerodynamic particle sizer. So to test the separator, we generated polystyrene particles ranging from 0.5 microns to 3 microns, and then drawing it through a microchannel with and without the separator design. And shown here is the data, and you can see that this experimental data matches quite well with the console simulation results. And to test the detector, we generated 1.5 micron particles at different concentrations, and then compare the detector count with the reference instrument count. So this is the data shown for with 1 minute sampling time. you can see that the detector count has a much lower efficiency than the reference instrument, and this is because we're using the optical, the power of a laser is much lower, and the sensitivity of a photodiode is it's much less sensitive than the reference instrument. However, the data shows a good linear correlation between the APS counts and the detector counts. So in conclusion, we have demonstrated a simple microchannel based impactor design to capture airborne particles larger than 2.5 microns. The experimental penetration efficiency curve agrees with COMSOL simulation results. The optical detector shows a linear correlation with the commercial particle detector. And the separator was integrated with a low-cost optical detector. So this is shown on the right. And so we can use this the separator as a disposable cartridge that plugs into the detector. So this was shown to work for up to 1 micron. However, unfortunately, our reference instrument was shipped out back in April, so I wasn't able to collect additional data. So this needs to be further validated in the future. So now I would like to thank the sponsors of this project, and thank you all for your attention. It's dependent on the velocity, yes. So I'm not sure I'm understanding the question. Right, right. Yes, potentially that could be possible. But so mainly we're using this to capture everything greater than 2.5, but there's definitely different options to explore whether to maybe capture smaller particles, so we can just use that, whatever's in the trap, to test that, and because then we would know what size it is by, like you said, by scanning the different velocities. That's a good point. So right now we are targeting this to be a disposable system because it's very easy to manufacture, but I think it would be very difficult to use air to just flush whatever is stuck, because the adhesion between the small particles and the wall might be too much. But I've tried flushing it with liquid, and it seems to be able to clean the channels quite well. Exit channel, do you mean the outlet, or? So, so this is because of the simulation parameters. So in the real case, the particles would just be moving out of the channel. So you mean at the entrance of the nozzle, of the exit nozzle? Oh, after. Right. So in terms of the dimensions, the particles is much smaller than the channel we're using. So so it might not have it. So particles might accumulate, but it won't have a significant effect. Hopefully, we're not sure about that at this point. And but I think, yeah, over time this device would need to be replaced, I think. So there could be some clogging issue here.
Thank you very much.
Yeah. Thank you.